Alright, today we're going to talk about one sample z-intervals for proportions. We're going to first review a one sample z-interval for means, which we talked about last week. Our formula for one sample z-interval for means was just x bar plus or minus z star times sigma over the square root of n. Remember that we used a one sample z-interval when we knew sigma, the population standard deviation. Now, today we're going to talk about a one sample z-interval you can set up for proportions. Now, when you do a confidence interval for proportions, this is like polling. If we're talking about like the Democratic primaries, and we said that Hillary Clinton had a confidence interval between 54% and 66%, that would be a z-interval or a confidence interval for proportions. We have a value with a margin of error. Now, a one sample z-interval for proportions is also known as a one proportion z-interval. You can call it that too. And the formula for a one proportion z-interval or a one sample z-interval for proportions is p hat, the sample proportion, plus or minus z star times the square root of p hat times 1 minus p hat divided by n. You may recall that the margin of error is the stuff after the plus or minus sign, so that would be z star times the square root p hat times 1 minus p hat over n. Make sure the square root is over this entire fraction. And then the standard error is just the stuff after the z star. So the standard error is just this square root of p hat times 1 minus p hat over n. Now, to set up a one sample z-interval for proportions, we're going to use a lot of the same steps that we used the other day for confidence intervals. Let's start off with our step 1, procedure, parameter, population. Our procedure can be called the one sample z-interval for proportions, or remember you could also call it a one proportion z-interval. The parameter is the value that we're using to describe the population. If we're talking about proportions, the parameter we're using is p, not p hat. P hat is your statistic. P is your parameter, and p is the proportion of all whatever you're working with. Voters who choose a certain candidate, for example. This is where your population comes in as well. So proportion of all, this is your population, who, and then whatever this population is voting for is essentially the finishing part of your parameter. So the P is the proportion of all, whoever your population is, who, whatever the parameter is. Check conditions. Condition 1 is the same condition that we dealt with the one sample z, one sample t, matched pair t, two sample t intervals, random sample from the population. Now our other two conditions are a little bit different this time. Our second condition is that the population is at least 10 times the sample size. You may recall that this is the same thing as rule of thumb 1 that we talked about back in chapter 9. We had also kind of used this notation that the population, capital N, is at least 10 times little n. The other condition that we're going to need to check is this, and it's a series of formulas. We need to verify that n times p hat is greater than or equal to 10, and we also need to verify that n times 1 minus p hat is greater than or equal to 10. This resembles something we talked about in chapter 9 as well, except in chapter 9 it was n times p and n times 1 minus p. What's the sense in checking this? Well, you'll notice we didn't use the second condition that we used for all of the confidence intervals for means, which was either the population was normally distributed, large sample size, or the normal probability plot is approximately linear. Why not? Well, in this case here, if these formulas work, it means that we do have a normal population. We use these similar formulas in chapter 9. Now in chapter 9 it was n times p, but in chapter 9 the reason we checked this was if these formulas worked, our sampling distribution was approximately normal. Here, if these formulas work, it basically is telling us that the population is normally distributed. It also usually means that we have a large sample size. In order for these formulas to work, n has to be pretty big. If n is like 6, this formula is probably not working out. If n is like 100, it's not a problem. As we move on to the back side of your notes worksheet, step 3, when we carry out procedure, remember that our formula that we're working here with is p hat plus or minus z star times square root p hat times 1 minus p hat over n. When you're carrying out the procedure, you do not have to write out the formula, but you do have to plug the numbers in the right spot. Because it is a z interval, we do not use degrees of freedom for z interval problems. We only use degrees of freedom for t interval problems. When you interpret your results, you know the drill. We are, whatever your confidence level is, we are blank % confident that P, we're making an estimate of what the true population proportion is. And then we're going to repeat what P was, basically plagiarizing from step 1. P is the proportion of all blank who blank is between the two values that you came up with on your confidence interval. These values will typically be percentages. We usually write them as decimals, so if it's 75 and 85%, we'd usually just write 0.75 and 0.85. I'd like you to go try problem 12.9b. You'll find this in your textbook. It's one of your homework problems for tonight. When you're done, check your answer with the substitute teacher. They will have the answers to this problem, and if this problem is looking good, then you can move on to your homework for tonight. Best of luck.